Okay, welcome back everyone. This will be the first lesson on related rates. Okay, this first one will be relatively short, just kind of really talking about what related rates are and this practice of using implicit differentiation with respect to t. Okay, so related rates, as the name implies, it's looking at how two or more rates of change or derivatives are related to one another. These are usually done implicitly with respect to time. We're looking at how does one quantity change per unit of time compared to some other related quantity per unit of time. For example, suppose, we have a perfectly circular snowball, okay? And as the snowball starts to melt, what's going on with the volume? Well, the volume is getting smaller, right? The volume of that snowball is decreasing, but so would be, say, the circumference and the diameter of that snowball. And there's probably a relationship between the rate at which, say, the radius is decreasing and the radius in the rate at which the volume is decreasing, okay? Or like suppose we have two ships, one traveling east at 4 kilometers per hour, another one traveling north at 3 kilometers per hour. Well, at what rate would the distance between these two ships be increasing? As the ships get further and further up and out to the right, obviously this hypotenuse becomes bigger and bigger. Well, at what rate is that itself increasing, okay? So, in the physical world, as one quantity changes per unit of time, it usually has an effect on another one, and that's what related rates is looking at. As one quantity changes per unit of time, how does some related quantity also change per unit of time? Okay, now this whole business of taking derivatives with respect to time t it's just implicit differentiation, right? When we have y equals x squared and we're told to find dy over dx, well, we write the derivative of y as dy over dx, and on the right hand side we would just write 2x, okay? We're taking the derivative of y with respect to another variable here. That's when we write this notation. Well, now what we're going to be doing is we're going to be taking derivatives of all sorts of functions with respect to t. And most of the time, we're not even going to see the letter t in our equations. So for example, let's just do a little practice now, taking derivatives with respect to t of some fairly familiar formulas. So in the first one, we have the area of a circle formula. Area is pi r squared. Again, if I happen to have some circle, maybe it's a pool of water where something's leaking on the floor and this pool of water is getting bigger, there's going to be a relationship between the rate at which the area is increasing as well as the rate at which the radius is increasing. Okay, well, here's how we take the derivative with respect to time. So the derivative of a, if you think about it, would just be like, if that was an x, the derivative would just be 1. If that was the letter y, the derivative would be 1 dy over dt. So the way we take the derivative with respect to t is like this. I would say, well, the derivative of a is just going to be 1 dA over dt. And that represents the derivative of the left side, the derivative of a, with respect to time. No different like when we take the derivative of y and simply write dy over dx, okay? On the right-hand side, pi is a constant, r is the variable. So we're going to apply the power rule here, bring down the 2, reduce 1 from the power, and again, because we're taking the derivative of r with respect to t, we multiply it by dr dt. Okay, this is the implicit differentiation with respect to t. When we do related rates problems, we are always going to see these in our derivatives. And what now this says is the rate of change of the area with respect to time is equal to 2 pi times the radius at that moment of time times the rate of change in the radius. That's the rate of change in the radius. This represents the rate of change in the area. And we can see that they are indeed related to one another. Okay. Next up, we have Pythagorean's theorem. So we want to take the derivative of this with respect to t. Again, really just the power rule here. I'm going to bring down the power, subtract 1 from the power, and then times, in this case, dA over dt. Similarly, bring down the power, subtract 1, times, in this case, dB over dt. And as you may imagine, going to get something pretty similar here. Okay, and that's what the derivative of Pythagorean's theorem with respect to time would look like. Again, the key being making sure that we're multiplying by these implicit parts. Okay, number 3, if you don't recognize that, that's volume of a sphere. If I want to take the derivative of this, volume is 4/3 pi r cubed. The derivative then on the left is just going to be 1 dv over dt. The rate of change of volume per unit of time is equal to, on the right using the power rule, I bring down the 3. Well, what do we end up with? 4 times 3 is 12, divided by this 3 is just 4. Pi r squared times dr over dt. So the rate of change of the volume of the sphere is equal to 4 pi r squared times the rate of change in the radius. And one more of these. Here we have volume of a cylinder. Volume equals pi r squared times h. This is probably the most involved of the ones we looked at, because what do you suppose we're going to have to use on the right-hand side? Since we're multiplying variables over here, we're going to have to use the product rule. Okay, so again, on the left, the derivative is just 1 dv over dt. Going through the product rule, here's my u and v pieces. U prime, 2 pi r times dr dt. That's the derivative of the u portion, times the v portion, plus the derivative of the v portion, we would write that as 1 dh over dt, times the u portion, pi r squared. And so the rate of change in the volume of a cylinder is dependent on both the rate in change in the radius as well as the rate of change in the height and the values of r and h at that specific moment in time. Okay, but again, really the idea here is try to get a sense of how we take derivatives implicitly with respect to t. So we're always getting this d whatever over dt back to represent the derivative of that particular variable with respect to time. Okay, we'll start getting into some problems shortly. The thing to remember is a lot of these are going to be like word type problems. So as you're reading through problems, the thing to really note here is that anything that's changing, okay, the boat is moving at this speed, the ladder is sliding down the side of the wall at this rate, something is increasing or decreasing, anything that is moving that's per unit of time represents a derivative. Okay, that's what a derivative is. It's a rate of change and it's per unit of time. Meters per second, kilometers per hour, okay, miles per hour, something along those lines, all right? So let's take a look at a couple quick problems here, and then in the next lesson I'll go through some more detailed ones, okay? Suppose a particle moves along the curve given by y equals x squared minus 3x plus 1. So we have this parabola, a particle just happens to be moving along this parabola. We're told that dx dt is 2 centimeters per second, okay? This is a rate of change. This represents the rate of change of side x. Actually, I'll say the rate of change in x, okay? That's the rate of change of x, dx over dt, okay? Find dy dt. So we want the rate of change in y at the instant x equals 1. Okay, so since we're dealing with rates of change, we're going to want to take the derivative of this thing with respect to t. So on the left, we're not going to write dy over dx. Now we're going to write 1 dy over dt equals. Now the derivative of x squared would be 2x to the first, but again we got to multiply by dx over dt because we're taking the derivative with respect to t. The derivative of negative 3x would be negative 3 times dx over dt. The 1 is a constant, so that goes away. But now we have our derivative. dy dt is 2x dx dt minus 3 times dx dt. And now what I can do is I can figure out what this equals now when x is 1 and dx dt is 2 by subbing in. Sub 1 in for x and 2 in for dx dt. And it looks like we're going to get 4 minus 6 would be negative 2. And the rate units are going to be the same, centimeters per second. All right, so x, is moving in the positive 2 direction, presumably to the right here. We're going to talk more about direction of motion in later units. Okay, but if dx is positive, it's an indication we're moving to the right. If dx is negative, we're moving to the left. What does the fact that dy came back negative tell you about the direction of motion? Chances are the particle's also moving in the downward direction because of the negative rate of change of y. Again, that's a little bit more than you really need to understand at this stage of the game. As long as you can follow the computations and get this answer, that's where you need to be today. Next up, similar, suppose a particle moves along the circle given by x squared plus y squared equals 25. At what rate is x changing if dy dt is negative 3 meters per second and the particle is at the point negative 4, 3? Okay, so we're moving along a circle centered at the origin, radius of 5. Dx is what we're looking for. At what rate is x changing? We want the rate of change in x. We want the value of dx dt here. Okay, we're told the rate of change of y, and we're given a coordinate. So again, we start with our basic equation. If we're dealing with rates of change, we take the derivative. So taking the derivative of x squared with respect to t, 2x to the first times dx dt, plus the derivative of y squared, 2y to the first times dy dt. The derivative of 25 being a constant would be 0. Okay, and now we can go ahead and sub in what we know and solve for what we're looking for. So it looks like the x coordinate is negative 4. We're looking for the value of dx dt. The y value was 3, and dy dt was negative 3. And so we end up with negative 8 dx dt minus 18 equals 0. So negative 8 dx equals 18. And so we get negative 18/8, negative 9/4 if you prefer, meters per second. Okay, so again, just kind of a short introduction to related rates. We're certainly going to go through some more advanced problems in the next videos, okay? But this should get you just kind of the whole idea of taking derivatives implicitly with respect to t. Again, we're always getting this sort of thing showing up. And, you know, the nice thing is you don't really need to memorize a bunch of formulas. Typically, they'll either be given to you, the ones you need to start with, or, you know, obviously you can look all these formulas up this year. So, okay, so don't worry about memorizing volume formulas and things like that. That's not the point here. Get used to taking the derivatives, subbing in what you're given. And, you know, also, try to be, you know, good with the reading. You know, when they say, hey, at what rate is x changing, we're looking for the rate of change of x. We're looking for dx dt. Okay, more to come shortly. Reach out if you have questions. Take care.